Hi, everyone. And thank you for joining me for the last session of the day before the evening party. I'm Andrei Pangin, Principal Engineer at Java Runtimes team at AWS. Besides work on OpenJDK, our team develops observability and performance-related tools, with Async-profiler being a prominent example. By the way, how many of you are already aware of Async-profiler? Great. Wonderful. As many of you are already aware of Async-profiler, I'm not going to spend much time on basics like what flame graphs are, etc. Instead, let me focus on less obvious problems and solutions. We'll start with a short introduction to Async-profiler anyway. We'll get to know its instrumentation capabilities. Then I'll show how recently added features help in solving new class of problems. Most of my presentation will be a live demo, so anything can go wrong. When talking about performance problems, the first thing developers typically imagine is a sudden CPU spike or CPU utilization topped at 100%. While this is indeed a common case, at the same time, it's not the hardest problem. It's probably the most straightforward to approach to. You just take CPU profiler of your preference, run it on an affected application, and get a flame graph showing what's going on. In practice, however, performance issues are not limited to just CPU bottlenecks. At Amazon, during JVM consultations, we hear customers asking a lot more questions. Developers are worried about latency of their requests, which are often caused by long JVM pauses. Application starting to learn is another common type of problem. Or memory leaks is another common pain point. I'm not talking about memory leaks in Java heap, which are also more or less straightforward to address with the heap dumps, but rather memory leaks besides Java heap. Today, I'm going to show you how to analyze such performance problems with Async-profiler. Async-profiler is an open source tool. I'm a lead of the project, so don't expect me to be unbiased. You can get binaries on GitHub or compile it from sources. A major version 4.0 has been recently published just a month ago. It has tons of new features and enhancements. For a long time, Async-profiler was described as a sampling CPU and heap profiler for Java, featuring JVM internal APIs and Linux perf events. While it was an accurate definition since appearance of the project, it covers only a small part of what modern version of Async-profiler can do today. First of all, it's not always sampling. It also has instrumentation capabilities, as I will show you today. It's not only about CPU and heap profiling. There are a lot more things that Async-profiler can do, starting from low-level hardware performance counters to JVM-specific things and memory leaks. Then, for Java, while it was originally designed as an accurate Java profiler, because of its ability to trace native stacks and non-Java threads, it made a tool capable of profiling non-Java applications as well. You can actually find an open source Rust agent based on top of Async-profiler for profiling Rust applications. Historically, Async-profiler relied on internal JVM function, async-get-call-trace, to get Java stack traces. And the project even got its name after this function. However, Async-profiler is now phasing out usage of async-get-call-trace in favor of its own stack working mechanism because of their stability issues with async-get-call-trace. Finally, Linux perf events is not an exclusive source of profiling events. For example, inside a container where perf events are often restricted, Async-profiler automatically switches to a per thread CPU clock as an alternative sampling mechanism for CPU profiling. Okay, enough theory. In a basic and most common case, you just run sprof command line utility, telling the event profile, CPU in this case, duration 30 seconds, and output file name. And in half a minute, it will give you a nice flame graph out of the box. Instead of -c CPU, you can actually put many other things, as I will show today. Okay. Let's all examples I'll show today are inspired by real issues found with customer environments in production. However, I intentionally simplified them. So once a customer complained about long GC pauses, and once they turned on GC logs, they quickly realized that there is something going wrong because there were full GC in the logs, whereas developer was absolutely sure they never call system GC in their code. In fact, since it was an educated developer, they've read blog posts about 1 billion row challenge, etc., and they tried to benefit from zero copying when reading files, and therefore, instead of reading files into allocated byte buffer, they decided to use memory mapped files, which was supposed to work well. So in a small program, which essentially scans a directory for all available files and reads them and processes somehow, no matter how. And it turns out that in this simple code, something called system GC, how to find where this full GC comes from. And that's where Async-profiler can help. I can start it the same way as for CPU profiling, but instead of putting -c CPU, I specify GVM underscore GC. It's not a special event that Async-profiler has. It's just the name of a function inside the GVM, which is called whatever GVM does full garbage collection. By default, it profiles for 60 seconds, but I don't need to wait for so long. Just can interrupt it at any time and see what I got. Yep. And here it returns as a flame graph that it's kind of trivial flame graph. There is the only place where system GC is called. And it comes from file channel map internal, somewhere from inside the GVM. Wait, does it mean that JDK itself calls system GC? Yes, it does. You can go to JDK source code, and yeah, here it is. In some conditions where an out of memory occurs, they try to handle this out of memory exception by calling system GC, doing thread sleep, and retry an operation. Who could imagine the JDK does it? Okay, but we've never seen out of memory error, right? Where does it come from? That's again where Async-profiler can help to answer such kind of questions. Now, instead of CPU or GVM-GC, I put another type of event. Again, it's not a special event, it's just name of a Java method that Async-profiler can instrument. So in this case, we want to find all places where out-of-memory error is created. And -c stack VMX is a new option appeared in version 4 that makes stack traces especially verbose, which with interleaved native and Java frames, with all intermediate JVM frames inside. Let's see how it looks like. Yep. So yeah, now it tells us where out-of-memory error is thrown. And it is thrown from the GNI code inside the GDK Unix file dispatcher impl in a function that does memory mapping, mapping a file. And the reason why it fails is because there is an option in Linux kernel called VM max map count that limits the maximum number of mapped regions that an application may have. And since the application created a new mapped region for each file it scans, and at some point the number of regions exceeded this limit, and syscall failed with an error. But there is no explicit way for an application developer to unmap those mapped byte buffers. The only way is to call garbage collection, and that's what GDK does. Fortunately, since GDK 22, we now have Project Panama with its memory segment APIs, where there is possibility to manage lifetime of mapped files directly, but it was still a preview feature in GDK 21. Okay, once a developer fixed this problem with reading files through mapped byte buffers, and they ran the application that scans files on the class path, and came across another issue. Now, everything looks good with GC. There are no long GC pauses. The heap size stays the same. And everything looks good from GC logs. However, when looking at the Java process at the operating system level, from the top command, we see that the resident size of the process constantly increases, meaning that Java takes more and more memory from the operating system, while heap doesn't increase. What can go wrong? Well, there is a built-in GDK feature called native memory tracking. To save time, I will not run it now on this application, but you can trust me that it will not show the cause of this memory leak either. But what can help us in this case is, again, Async-profiler and its new native mem feature. In version 4.0, we've got another type of event called native mem, which instruments C-level allocations, all malloc, calloc, realloc, and related calls, and provides you with a flame graph showing where all these allocation functions come from. This includes both the JVM code, like you can here see GC threads, VM threads, and application code. Native memory is allocated from implementation of inflator, random access file, zip, etc. But if something allocates memory, it doesn't yet mean there is a leak, because this memory can be freed immediately, right? How to understand what memory is freed and what is not. To find this out, we can retry running our native mem mode, but now choose GFR as an output format. The difference is that in GFR format, Async-profiler stores all events. It doesn't aggregate on the fly. So it stores all memory allocations and all places all facts of where this memory is freed. And then running a post-processor, there is a GFR-conf tool included in the Async-profiler bundle that helps you to convert GFR recordings to flame graphs. Native mem option says that we'll process native memory allocations. Leak option says that GFR converter will match allocations of memory with the related free calls. Total will count total allocated size in bytes versus number of allocations. And finally, lines option will help you to navigate the code by adding line numbers in a flame graph. Now, if you see our new flame graph, now it's unambiguously shows the single place in the code where malloc is called, which is not apparently freed. And this comes from a files.list call in our class path scanner code at line 103. Yep. If you go to line 103, by the way, IDEA highlights this is a potential error. It says that stream path is used without try with resource statement. And this is indeed where the error is, because files list returns us a stream which needs to be closed. But we don't close it here. And even though the Java object can be freely garbage collected, the associated native resources are not freed. So the fix is simple, is to wrap this stream into a try with resource statement, like here. But there is another thing with this application that I would like to show you. There is actually another type of a leak. If you observe the number of open files by the Java process, we can notice that it also constantly increases. And depending on our system limits, we may either hit a file descriptor limit first or the available memory limit first. But there are many ways how file descriptor can be created in Linux. How to find where it is created in our Java application. Let's call Async-profiler again. It has a capability of tracing functions inside Linux kernel. These are called key probes. If I try to run straight away, it will fail because profiling Linux kernel requires to be a privileged process. So we add two options. First, run our profiling command under sudo, and then add fd transfer magic option. What it does, it offloads creation of perf events to a separate privileged process. The reason is that Async-profiler works in the context of the application being profiled. And even though we started as prof as sudo, our target application still runs under unprivileged user and cannot profile Linux kernel. But fd transfer option allows to work around this problem. So there is a function in Linux kernel that is called every time a new file descriptor is created. And we go to look at the result. Again, it will point us to the same very place in files list. So the new file descriptor is created when a directory is opened for traversing files. Good. Okay, as we saw, besides usual profiling modes, CPU, walk log profiling, allocation, and log, we can instrument invocations of Java methods native functions, both inside JVM and in third-party libraries. We can profile Linux internal functions, and there is a special option for finding native memory leaks. Native memory profiling, not to confuse with native memory tracking in the GDK, has an advantage that it can be enabled at runtime. It doesn't require any JVM options at startup. And unlike native memory tracking, it profiles not only allocations in the JVM itself, but also in the GDK class libraries, in the third-party GNI code. And it can be as well combined with other profiling options. So you can do CPU profiling and native memory profiling at the same time, as long as your output format is chosen as GFR. And to reduce the potential overhead of this native memory profiling, you can set a threshold. So like if I put native mem 2 megabytes, then only one sample per 2 allocated megabytes will be collected. All right, we've seen how Async-profiler helps to solve ongoing issues. But what if a problem has happened in the past? It would be nice to have a solution that allows us to troubleshoot issues after the fact. And yes, the name of this solution is continuous profiling. Actually, Async-profiler already has a built-in option for continuous running profiler continuously. Like if you add loop option, it will restart profiling every 1 hour and produce GFR recordings with a given pattern. For a reasonably large application, all these files can take up to several gigabytes per day. How to analyze all these files? And as a solution for this problem, we've developed a new visualization mode called heatmaps. The idea was borrowed from Brandon Gregg's Flamescope project. However, the Flamescope is more focused on a short time period of profiling, whereas Async-profiler heatmaps allow you to see the recordings, or whole day recordings on one screen. And another good thing about it is that this conversion of GFR to heatmap reduces the size of recording by almost two orders of magnitude, while retaining all the required information. So what is a heat map? It is essentially a two-dimensional timeline. On the horizontal line come hours or minutes, and on a vertical axis, seconds or milliseconds. And there is a third dimension, color. The brighter is the color, the more events happened in this period of time. So by quick glance on the heat map, you can easily notice that there were less activity at the night time and more activity in the daytime, which is quite understood, as well as anomalies are immediately seen. Let's take a look at some real examples from real applications. Yep. Here is a heat map of a real service recorded for 24 hours. As I said, there is a period of, with less activity in the night and a period of high activity. And this, there is something wrong in the middle. On the heat map, we can select any point in time and get a flame graph for this particular point in time. Or we can select an arbitrary time range and immediately build a flame graph for this time range. But it's hard to see what's wrong in during this anomaly comparing to the normal period. but it's easy with a differential flame graph feature. So we can select one region and compare it against the baseline and get a differential flame graph right away. With yellow color is the frames that appeared in the periods that we are interested in, that those frames were not seen in our baseline. In this initial view, every point denotes 5 seconds of profiling time, and every vertical line corresponds to 5 minutes. But we can zoom into it and get high resolution. Now, one point is 1 second, and one vertical line is 1 minute. We can zoom even further and go down to 20 milliseconds. And now see, we can literally see what an application was doing during the whole day with a 20 millisecond precision. And once we get to this level of zoom, we start seeing new issues that we didn't notice before, like this line where bright dots are interleaved with white ones. So what was happening here? A process was using all its CPU quota during a short period of time, and because of this, operating system throttled the process, put it on a pause. And that's why the next few milliseconds, it didn't receive CPU time. To find out what was the cause of this throttling, we need to look into the point right before a white period of time. And in this case, this will be about 70% of time was spent in non-blocking hash map. It's a customized version of concurrent hash map that was used some time ago in Cassandra. Now they switched to a different structure. And it turns out that under some conditions where many threads start competing for resizing this non-blocking hash map, there is high contention. So in our case, the fix was simple, to switch from this customized non-blocking hash map to a regular concurrent hash map, and the problem went away. The heat maps can be built not only for CPU profiles, can be as well built for allocation profiles. And here is an example. What I like about heat maps is that it nicely shows different periodic activities. For instance, here is something happening every 5 minutes. Also, we can notice those dotted lines. There's something happens every 10 minutes, and so on. We can filter and search on these heat maps. For example, searching for log4j, we will highlight places on our timeline where the code was, the most allocations happened with log4j in a stack trace. And that was exactly our anomaly that we can see in the middle. Okay. So to recap, the heatmap converter provides us with a single-page standalone HTML file. It doesn't require any server or something. You just take a single file, you can send it over email, share in tickets, etc. The resolution of the data can be as high as 20 milliseconds. And it's interactive. You can build instant flame graphs, build differential flame graphs, search and filter. On this positive note, I'd like to conclude my talk by saying that Async-profiler is not only a CPU and memory profiler. It's a multifunctional tool that combines multiple techniques. Like today, we learned about its instrumentation capabilities, native memory profiler, and heat map visualization. Thanks.